Hello and welcome to my part of our lab tour. My name is Cynthia Pillich and I'm a PhD student at the workgroup of Professor Heiko Wende. Together with the workgroup of Professor Wurm, we study the effect of high temperature exposure on planet formation. For this, we heat meteorites like this one, milled to dust, which looks like this, fine powder, in various atmospheres, and then analyze them with different experimental methods, especially via iron-57 Mössbauer spectroscopy. In this tour, I will show you our oven used for heating our samples and one of our iron-57 Mössbauer spectrometers. Although the formation of planets has been a field of interest for a very long time, its processes are still not fully understood. In our project, we study the behavior of meteorites exposed to high temperatures because they represent the early stages of a planet system. This is practical as we can execute experiments in the lab. Here we see a tube oven which can heat samples at temperatures up to 1200 degrees centigrade. Using an oil diffusion pump, we can reach a fine vacuum inside the tube. By opening this needle valve here, it is possible to let gas stream into the tube. By this means, we can simulate the conditions for dust particles in the early stages of planetary formation. Iron-57 Mössbauer spectroscopy is a very useful tool to study the magnetic structure of iron-bearing minerals, as it is non-destructive and has a very high sensitivity. With the help of this technique, we can reach resolutions of about 5 nanoeV. A cobalt-57 source emits gamma rays with an energy of 14.4 keV. Depending on the electronic and magnetic interactions inside our sample, we need to tune the energy of the gamma rays via the Doppler effect because they can change the energy levels, nuclear energy levels of the iron atom. If the energy equals the energy gap in the sample, the gamma rays can be absorbed recoil-free. There are 3 major hyperfine interactions which can be resolved via Mössbauer spectroscopy. The valence state of the iron atom can cause a shift of the absorption line. This is called isomer shift. A non-zero quadrupole moment splits the absorption line into 2 peaks and gives us information about its local symmetry. An interaction with an intrinsic magnetic field gives a rise to a sextet. So gamma rays are emitted by the source and hit the sample. Rays that don't match the energy gap can pass through the sample and are detected by a proportional counter. So we will see a negative signal every time absorption conditions are met. In this lab we see several different iron-57 Mössbauer setups, and I will be focusing on this setup here. The sample is mounted into a closed cycle cryostat. Helium gas is pumped with high pressure into the cryostat where it expands and cools down the sample down to 4 Kelvin. Therefore there is no need to fill the chamber with liquid helium. Now I want to show you some actual results we got from our meteorite powder. As you can see, the spectrum here is very complicated with many subspectra. Also, one of the constituents is represented by 2 octet structures because the iron in that mineral has very distorted surroundings. Nonetheless, it is possible to identify every iron-bearing mineral in this meteorite.